All right, this is two lessons in one right now. It's lesson LO5 and LO6 on locuses. This is the last of the lessons on locuses. Okay. The last locus theorem is locus theorem 5. It's about equidistant from two intersecting lines. So it says the locus of points equidistant from two intersecting lines, K1 and K2, is a pair of angle bisectors that bisect the angles formed by K1 and K2. Alright, if you look at this diagram, we actually have to change something on here, right? Because the name of the lines is wrong. They're calling it L2 and L1, and the way I have it labeled in the question is K1 and K2. So K1 and K2 are these intersecting lines. And if we want to think of all the points that are the same distance from those two lines, it would be all the points directly in between these two sides, directly in between the bottom two sides, directly in between these two sides, and directly in between these two sides. So what happens is you have two intersecting lines that are the angle bisectors of these angles. It means it cuts these angles in half. Okay? It's called equidistant from two intersecting lines, and these are the two intersecting lines. So let's look at this consider problem. Indiana Jones is searching for a treasure. His treasure map shows a V-shaped canyon. You can see the V-shaped canyon right here with the two cliffs, formed by two vertical cliffs. The directions state, start at the point where the cliffs converge. That's right here, okay, where they come together. Walk through the canyon staying in equal distance from each cliff. Can you picture the path he needs to take to satisfy these conditions? So if he's going to stay directly in between these two cliffs, obviously he has to walk in between them. Alright? So the angle that's formed by these cliffs is bisected by his path. And if you added up all these points that he would have to walk, essentially, it would form a line directly in between those two lines. This line is the angle bisector of these two lines here. It cuts it in half. It's right in the middle. So the dashed line, in this case it's actually the red line, so let's cross that out. The red line represents the locus, which is equidistant from two cliffs. This line is the bisector of the angle formed by the two cliffs. Any point on this line is the same distance from each cliff. A compound... Alright, now we have put a little line here. There should be a division here. Alright. On your copy, this will probably be on the next side. I'm going to fix that. Alright, this copy got messed up on the printing. So this should be actually on the next sheet for you. But let's read it anyway. A compound locus problem involves two or possibly more locus conditions occurring at the same time. The different conditions in a compound locus problem are generally separated by the word and or the words and also. And we'll see examples of that. Okay? Also, in your copy, if this was done in black and white, I'm not sure if the color printer is going to be available. So this line in the middle is what they're talking about as the red line. In fact, let's label it red line so that we know what we're talking about in this problem, red line. So let's turn this over or go to the next sheet and we'll talk a little bit more about compound locus problems. If two locus conditions exist in a problem, which is called a compound locus, prepare each condition separately on the same diagram. Okay, let's underline that. That's important. After the two conditions are drawn separately, count the number of points where the two loci conditions intersect. It may help to draw the locus locations as dotted lines and then find where the dotted lines cross. These are the steps you would follow in a compound locus problem. Draw a diagram showing the given information in the problem. Read carefully to determine one of the needed conditions. Look for the possibility of the words and or and also separating the conditions. Plot the first locus condition. If you do not see one of the locus theorems at work in the problem, locate one point that satisfied the needed condition and plot it on your diagram. Then locate several additional points that satisfy the condition and plot them as well. Plot enough points so that a pattern or a shape is starting to appear, or until you remember the needed locus theorem for the problem. Through these plotted points, draw a dotted line to indicate the locus or path of the points. Repeat steps 2 through 4 for the second locus condition, And where the dotted lines intersect will be the points which satisfy both conditions. These points of intersection will be the answers to the compound locus problem. All right, now let's go to the next sheet or the other side. Okay, we have one more of these consider types of questions. So a treasure is buried in your backyard. The picture below shows your backyard, which contains a stump. Here's the stump down here. A teepee, it's a weird backyard, and a tree over here. The teepee is 8 feet from the stump. You see the distance is 8. And 18 feet from the tree. This distance is 18. The treasure is equidistant from the teepee and the tree. And also 6 feet from the stump. Okay, locate all the possible points of the buried treasure. So let's look at the answer. Okay, let's label this as red line. The red line represents the locus, which is equidistant from the teepee and the tree. Remember, that was the first question. It said the treasure is equidistant from the teepee and the tree. Here's that and also part. So this is the first locus condition. Equidistant from the teepee and the tree. And also 6 feet from the stump. So we're working on the first part. Equidistant from the teepee and the tree is a line directly down in between those two. And that's what this line represents. Okay? It's the bisector of this segment. The perpendicular bisector. Alright? Now, the blue circle represents, okay, this didn't come out blue, but it's supposed to be the blue circle. The blue circle represents the locus, which is 6 feet from the stump, right? Because it also said 6 feet from the stump. That's a circle with a radius of 6 feet. So the radius is 6 feet. The treasure could be buried at either X location. So what we do is we mark X's where the two locus or the loci intersect. Okay? Those are the only two possibilities for where the treasure could be. The red line and blue circle could have been drawn dotted to indicate they are the locus locations. And when you do these types of problems, you'll draw them dotted, and you'll see what that means, how to do that. Okay, let's look at the examples. Okay, first it says the locus of points equidistant from two intersecting lines. So what we have is two intersecting lines. They want to know all the points that are equidistant. So all these points that go like this are the same distance from these two lines, right? They're always the same distance. And then all the points that are directly in between these two vertical angles are also equidistant. So what you do is you draw a dotted line as best you can in between both of those angles. Like that. And like that. Okay? So it is a pair of angle bisectors. Okay? What is the equation of the locus of points equidistant from the x-axis and the y-axis? So what we do is we take a piece of graph paper, fold it in half. Okay. Let's just keep it folded in half. Let's see. Okay, there we go. So I'm just using the bottom half of my sheet right now. I'm going to draw, or the top, whatever, it's one half, not the bottom or the top, doesn't matter. Okay? In fact, I'll make this the top of my sheet. So you want to put your name in the top corner, right? And you want to put what problem this is. This is example 2. So, we got one line for the x-axis, the y-axis, and let's draw x, y. What is the equation of the locus of points equidistant from the x-axis and the y-axis? Well, remember, it's an angle bisector, right? It goes directly in between the two axes like this. Directly in between. It cuts each one of these 90-degree angles in half. So I'm going to set my ruler up and draw dotted lines for the locus. That. Okay, those are my locus, and this is the line y equals x. Okay, if you don't know that, well, you have to know that, so make sure you remember it. A slanted line that goes from the bottom left to the top right, directly in between the axes like this, is y equals x. And this one that goes this way, right, it's going in the negative direction. So instead of this being y equals x, this is y equals negative x. And that's it for example 2. Let's look at 3. Ben skis through a park that is bounded on two sides by straight intersecting streets. Okay. Ben skis so that he is always the same distance from each street. Describe Ben's path. So this is the same deal. What we have is two intersecting streets. Ben skis that he is always the same distance from each street. So let's say he's skiing like that. He has a few choices. He can be going here, or he could also be going through them this way, right? So Ben will ski along a straight line, which is the angle bisector of the angle formed by the two streets. So depending on which way he's going, he would be on one of these dashed lines. Number 4, true or false? The locus of points equidistant from the sides of an angle is the angle bisector. So if we have an angle, the locus of points is the angle bisector. That's true. Okay, turn this over or put it aside. Put your name on the top, by the way. Put your name on top of all the sheets. I don't know if I reminded you to do that, because if I get a sheet that doesn't have your name on it, I just throw it out. Okay. So here's what we're on now, example 5, and we're going to do this one on a graph. So I'm going to do it on the bottom of this one. What is the number of points in a plane 2 units from a given line and 3 units from a given point on the line? So this is example 5. It's 2 units from a given line. Alright, so let me draw the given line. That's our given line. 2 units from a given line. That's the first locus. I'm going to go 2 units down. And I'm going to go 2 units up. Okay, that's the first one. Then here's our connecting word, so we know it's a compound locus. And 3 units from a given point on the line. So put your point anywhere, and it's got to be 3 units away. 1, 2, 3. So it's a circle, right, with a radius of 3. So I'm going to use my compass and draw this circle. I'm going to line up on one of those dots that's 3 units away. Okay, there you go. So it says, what is the number of points? And the circle you can't draw dashed, right, because you're using the compass, so don't worry about that. There's one intersection point, 2, 3, 4. 4 points. Okay? So that's example 2 and 5 on this sheet. Now let's turn it over. Fold it up. Example 6. Two points A and B are 6 units apart. How many points are there that are equidistant from both A and B, and also 5 units from A? So A and B are 6 units apart. So I'm going to put A right here, and I'm going to go 6 over. 1, 2, 3, 4, 5, 6. And I'm going to put B. How many points are there that are equidistant from both A and B? That's the first part. Okay. All the points that are equidistant, remember, equidistant from 2 points is a line directly in between them, just like that. This is the locus of points equidistant between 2 points. Okay? And we know that this is equal to this, and this is a perpendicular bisector. And so we know there's another locus we have to draw, and it's 5 units from A. So we got to go 1, 2, 3, 4, 5. It's going to be a circle 5 units from A. All I need is that 1 point. I'm going to line my compass up on it. Okay. How many points are there? So there's 1 right here, and there's 1 right here. So 2 points. Okay. So now on the bottom of that, let's do 7. Parallel lines R and S are 8 meters apart. Okay. So let's draw these 2 parallel lines. I'm going to draw them vertically. It doesn't matter how you want to draw them, as long as they're parallel. So this will be R, and then 1, 2, 3, 4, 5, 6, 7, 8. 8 units away is S. Okay, and A is a point on S, so I can put A anywhere I want. I'm just going to put it near the middle. That usually makes it easier. How many points are equidistant from R and S, and also, so the first one is equidistant from R and S. When you have 2 parallel lines, all the points that are equidistant from those lines run directly in the middle. So what we have is a locus like that. And now it says, and also 4 meters from A. Alright, every box in this problem is a meter. So I'm going to go 4 meters from, how many? 4 meters from A. 1, 2, 3, 4. And that's a circle with a radius of 4. And in my diagram, each box represents 1 meter because this problem is in meters. And look at this. We only have 1 intersection point. This dotted line is actually tangent to this circle, right? It touches it at 1 point. Okay? So, what did it ask me? How many points? So 1 point. Okay? So now that page is filled up. You got, oh, we didn't put example 7 here. So we got 6 and 7 on the back. And on the front we got 2 and 5. And your name needs to be on it. Then you can put that sheet aside. Alright, now we're going to need another sheet for 8. A given point is 10 units from a given line. How many points are 3 units from the line and 5 units from point P? So we're actually going to need the whole sheet for this problem. Alright, so make a nice... actually, we don't have to make anything. We can just leave the sheet as it is. I'm turning it horizontally, though. Let's see if I want to make it horizontal or not. No, I'm going to leave it vertical. Let's put our name. And this is example 8. Okay? Example 8. Let's see. A given point is 10 units from a given line. How many points are 3 units from the line and 5 units from point P? Okay, so I'm going to go down right about here and put my point. I'm leaving room because I know I am going to have to make a circle around that point most likely. Alright, so this is point P, and it's 10 units from a given line. So let's draw a line 10 units below. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now let's draw a line here. Okay. So that point and that line are 10 units apart. Now what does it say? How many points are 3 units from the line? So that's the first part. 3 units from the line. That would be 3 above the line. And I make a locus. Those are all points 3 units, but also 3 units below the line is another locus, because we can be 3 units away from that line by being above it or below it. Okay? Then it says end. So here's our second locus, 5 units from point P. Well, that's 1, 2, 3, 4, 5. That's a circle. With a radius of 5. Oh, look what happens. How many points are both 3 units from this line, which is these 2 dotted lines, and 5 units from P? 0. This circle does not intersect either one of those dashed lines. So the answer to this problem is 0 points. Okay? Now let's do example 9 on the back, which I also think we need the full page for. 2 points A and B are 7 units apart. How many points are there that are 12 units from A and 4 inches from B? That's supposed to be units, not inches. Okay, that's a typo. Now, there's 7 units apart, so, and 12 units from A and 4 units from B. So I'm going to make A pretty far down the page, actually. I'm going to make it like down here, and then I'm going to go A and down 7, 1, 2, 3, 4, 5, 6, 7, and I'm going to put B. Now it says 12 they're 7 units apart. That's what I just did. Then it says 12 units from A. So that means I got to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I'm going to have a big... That's why I made my point A pretty far down, because I knew I was going to have a big circle around it. It told me 12. So I'm going to move this until it's 12. Now you can see why I moved A down, because that's a big circle, and that's why we need this whole sheet. That's 12 units from A, right? And we also have And also 4 units from B. Okay, so I go to B. 1, 2, 3, 4 away. Oh, we have another answer of 0. Right? These circles do not cross. 0 points. Okay? We can put that sheet aside. And one more graph paper now. We got 1, 2, 4 problems left. And they're going to fit on this last piece. So let's put our name and example. And this would be example 10. Fold your paper in half. Okay, example 10. There's a couple of parts to this problem. Let's just take it one at a time. The locus of points equidistant from the points 4, 1 and 4, 5. So we do need a coordinate axis. There's my y. There's my x. Alright, so equidistant from 4, 1, 1, 2, 3, 4, 4, 1, and 4, 1, 2, 3, 4, and 4, 5. The locus of points equidistant from 2 points is the perpendicular bisector of the line containing That's it right there. It's directly in between them. If we were to draw a line between these 2 points, this dotted line would be perpendicularly bisecting it. So that's A. Let's look at B. Draw the locus of points equidistant from the points 3, 2. So 1, 2, 3, 1, 2. Let's label these so we don't get confused. A and B. So A, B, and now we'll do C and D. So this is C. And D is negative 4. 1, 2, 3, 4, 2, 1, 2. So the line directly in between those 2 points is actually right in the middle of, right in between 0 and negative 1. Okay, now, let me label that D. Let's keep going. Find the number of points that satisfy both conditions stated in A and B. Give the coordinates of each point found. So there's 1 point right here that satisfies. So let's put 1 point, and it says we also need to put the coordinates. Well, it's minus a half, so minus 1/2 or minus 0.5, whatever you prefer, and then I'm up 1, 2, 3, so minus a half, 3. That's our answer to that one. Okay? And then turn it over or go to the next page, whatever it turns out to be. We're on 11. We're going to do that on the bottom of this problem. Draw the locus of points 3 units from the y-axis and write the equation for this locus. So again, we need an x and a y-axis. Okay. Let's look at the first part. 3 units from the y-axis. And write the equation for this locus. So that would be 3 units to the right. And 3 units to the left. This is the line x equals 3, and this is the line x equals -3. Okay? Those are the equations. It said you had to write them. So look at B. Draw the locus of points 4 units from the origin and write the equation for this locus. Oh. So 1, 2, 3, 4 units from the origin, which is going to be a circle, right? And what's the equation of that circle? Well, remember the equation of a circle is x minus h squared plus y minus k squared equals r squared. Right? Where h comma k is the center, which in our problem is 0, 0, and r is the radius, and in our problem it's 4. So what do we have? We have x minus 0 squared plus y minus 0 squared equals 4 squared. That would be x squared plus y squared equals 16. So you can see how they put more than one topic into this problem, and they do that all the time on the Regencies. Usually the Regents questions are 2 or more topics in each one. Okay? So that's 2 problems, one on the top and bottom. Now let's turn it over and finish this up. The second to last problem, example 12. Alright, we have points again, so I need an x and a y axis. Okay. 2, 6. 1, 2, 1, 2, 3, 4, 5, 6. That's point A, and then we have 4, 4, 1, 2, 3, 4, 1, 2, 3, 4. So this was A. This is B. C is 8, 6. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. That's C. Now I'm just going to move B, because I think it's going to be in the way. I'm just going to move the label B down here. I think that'll be out of the way. Okay. Determine the points in the plane that are equidistant from all 3 of those points. Wow. Let's do A and B first. All the points equidistant from AB is going to be directly in between A and B. It's a line, because remember the locus of points from 2 points is a line that goes directly in between those 2 points. Now let's look at BC, which is also going to be, now this one goes right through here, and then it goes up like this. Down, wait, how does it go? This one, if this is the line, if this is the segment connecting B and C, right there, okay? See, what we just did is we bisected this segment first. Now we're going to bisect this segment BC. Yeah, that should be this. Yeah, that is. It's this line. Just like this. It's up 2 and left 1. Up 2 and left 1. And the reason why I know I'm right is because you can see it looks perpendicular. And if I wanted to pull out my protractor and check it, I could tell that it's 90 degrees. I could see that. See, I'm lining this up on this flat line. Right? And when I go up to 90, I can see that this line would extend directly to 90. So I know that that's right. Okay? I could also analyze the slopes if I need to, but I don't need to do that. Now, we also have 2 more points, right? We have A and C that we have to perpendicularly bisect. So A and C are 1, 2, 3, 4, 5, 6 apart. So right in the middle is here. And now you can see that they all meet at one point okay, and at this point right here. And what's the question asked? Let's go back again. Determine the points in the plane that are equidistant from the points blah blah blah. So we have 1 point, and let's put down its coordinate. 5, comma, 1, 2, 3, 4, 5, 6, 7. 5, 7. Okay? One more problem. Example 13. Equidistant from 2 points again. Alright, so I need an axis, an x and a y axis. Okay. Let me move that down a little bit. -5, -3. 1, 2, 3, 4, 5. 1, 2, 3. Let's call that A. And then I have 7, 5. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. Okay, so we're going to have to be a little careful now when we figure this out, because it's hard. We know it's the line in between these 2 points, but it's hard to figure out exactly how to line this up. Okay? And it wants to know the equation. Alright, so what we do is first we draw the line between the 2 points. Let's go right through those 2 points. Whoop. Okay? What's the equation of that line? The equation of that line is y equals, what's our slope? Well, we're going up 2 and over 3, up 2 and over 3, up 2 and over 3, up 2 and over 3. So we're going up 2, that means the 2 is on top of the fraction, and we're going to the right 3, and they're both positive because up and to the right are positive directions. And since we went to the right 3, the denominator is 3, because our x direction is 3. I mean the denominator, and our y direction is the numerator. So it's y equals 2/3 x, and then we look at where we crossed the y-axis, and you could see we crossed right here. Well, where is that? That looks like it's at about a half. Okay? But we actually don't really care what that is. Alright, well we can figure it out. How about that? Y equals 2/3 x plus b. Let's figure it out to make sure. Okay? Right now we don't know what it is, we know it's b. Alright, we want to solve for b. So take one of these 2 points. Let's take b since they're both positive. Which was 7, 5. And plug the 7 in for the x and the 5 in for the the 5 in for the y, and we'll solve for b. So we got 5 equals 2/3 times 7 plus b. 5 equals 14/3 plus b. I got to turn 5 into a fraction over 3, so let's make it 15 thirds. So 15 thirds equals 14 thirds plus b. Subtract 14 thirds from both sides, and what you get is b equals 1/3. So it wasn't a half, it was a third. Okay, so that's why we have to go through this process. So our final equation for this line, which isn't even the answer, is y equals 2/3 x plus 1/3. Now, what's the equation? What do you remember? We know that the locus is going to be perpendicular and right in between those 2 points. Now, I hope you remember something about the slopes of perpendicular lines, right? Let's write it down. The slopes of perpendicular lines are negative reciprocals and multiply to -1. Okay, the slopes of parallel lines, remember, if you multiply them together, you get -1. They're negative reciprocals of each other. So I know that this slope, 2/3, times the slope that I'm looking for equals -1. So let's multiply both sides by 3/2. By the way, guys, if you are having trouble with this algebra stuff, you really need to come to extra help, because this is something we don't have time to go over. This is something you're supposed to learn in elementary school and in middle school and in algebra. All right, and we just don't have the time for the Regents exam to go over this type of stuff. So this is something you have to come to extra help for if you don't know how to do this algebraic stuff. Okay? So 3/2 times 2/3 cancels out, and we're left with m equals -1 times 3/2 is -3/2. Okay? So our slope is -3/2. Now we have to see if we can find the point directly in between this line. Now it looks like it's this one, but let's count and check. From A, I go up 1, 2, 3, 4, and I go to the right 1, 2, 3, 4, 5, 6. So up 4 to the right 6. So let's see if the same thing happens. Because now if I have to go up 4 and to the right 6 to get here, and then I know this is right in the middle. Up 1, 2, 3, 4 to the right 1, 2, 3, 4, 5, 6. All right, so I know this is a point on the line, and my slope is -3/2. So that means I'm going to go down 3 and to the right 2. From this point, down 1, down 2, down 3, and to the right 2. Make a point. That's all you need, is 2 points to draw a line. So I'm going to line that up. Okay. And I'm going to draw a dashed line, because remember, this is my locus line, right? Okay. Now, there's my y-intercept, but I don't exactly know what that is. Alright, so I have to figure it out again. So I have y equals -3/2 x plus b. Right, this is my new slope. Let's take a point on this line. We can use this one right here, which is 1, 1. So let's use this as our xy. So 1 equals -3/2 times 1 plus b. 1 equals -3/2 plus b. Let's add 3/2 to both sides. b equals 1 plus 3/2. 1, let's change 1 into a fraction over 2. 1 is really 2 over 2. So 2 halves plus 3 halves is 5 halves. That's what b is. This point is up 5 halves from the origin. So let's finally write my equation down. Y equals negative 3 halves, that's the slope I found, negative 3 halves x plus my b is 5 halves. Okay? And that is the last problem for this entire unit on locuses. So good job and good luck.